Okay, on Friday, a few too many of you looked like you were deer in the headlights. And we were so rushed at the end that I forgot to remind you that there are two additional on your owns, and they are in your spiral book. So everybody open your spiral book right now to page 15, and I'm going to do on your own 2.10 with you. All right, so when we read this one, it says that a calorimeter has a mass of 9 grams and a heat capacity or specific heat, that C, is 2.31 joules per gram degree Celsius. The calorimeter holds 100 grams of water at an initial temperature of 25.1 degrees Celsius. All right, let's take that first sentence and fill in what data we know. All right, the first thing we know is the calorimeter. So the calorimeter has a mass of 9.0 grams, and the heat capacity of that calorimeter is 2.31 joules per gram degree Celsius. And in that calorimeter, in that cup, is 100.0 grams of water. 100.0 grams of water. Now they don't tell me the heat capacity, but water is one we're supposed to know. Well, remember the definition of a calorie. It's 1 calorie to heat up 1 gram of water, 1 degree Celsius. But we're not working in calories here, right? We're working in joules. We're working over here in joules. But that's easy enough because we know that 1 calorie is 4.184 joules. So joules per gram degrees Celsius. Okay, all right, so what else do they tell us in that first sentence? They tell us that the liquid, the water, starts at 25.1 degrees Celsius. So that's the temperature that the liquid starts at. All right, what happens next? So now we've got our calorimeter. Remember our styrofoam cups. There's 100 grams of water in there. This isn't styrofoam, but it's some other material, 2.31 joules per gram degree Celsius. Now we're going to put a hot metal in that liquid. How much metal? It's 43.2 grams. So the mass of the metal is 43.2 grams. And the metal starts, the initial temperature of the metal is 111.0 degrees Celsius. Now they're going to put that hot metal is dropped into the calorimeter, and the final temperature of the water is 29.1 degrees Celsius. And the question is, what is the specific heat of the metal? Remember, specific heat and heat capacity are synonyms. So this is what is the specific heat of that metal. All right, now all I've done so far is read the problem and translate what they've told me. All right, now all this in yellow is just straight off of the question. You have to be able to read those questions and figure out what they're asking you. Now we're going to do some thinking. Now we're going to, no calculations yet, just thinking. All right, so think about that styrofoam cup with the thermometer and the water in it. Well, if the liquid starts at 25.1 degrees Celsius, so does the cup, right? So the calorimeter is also at 25.1 degrees Celsius initially. Well, at the end of the experiment, the liquid has warmed up to 29.1. Well, if the liquid is 29.1, that's in contact with the calorimeter, so the calorimeter, the cup, is also 29.1 degrees Celsius. But what else is 29.1 degrees Celsius? The metal. The reason the temperature of the liquid quit rising, right? You put the hot metal in there, it starts to rise, and eventually it quits rising because the metal has cooled down to the same temperature. Oops, I don't know why that's messy there. 29.1 degrees Celsius. So at the end of the experiment, the metal, the liquid, and the cup all have the same final temperature. At the beginning of the experiment, the metal's hot and the liquid and the cup have the same initial temperature. All right, so again, I haven't picked up my calculator yet. I haven't done any calculations. I've just reasoned with what the data gave me. Alright, so now we're going to pick up a calculator. So now you can pick up your calculator. And hopefully, there we go. Alright, first thing we're going to do is figure out the change in temperature of the cup. Remember, change in temperature is always final minus initial. What did you end up with minus what you started? Well, I ended up at 29.1 and I started at 25.1, so my change in temperature of the calorimeter is 4.0 degrees Celsius. The exact same thing for the water, 29.1 minus 25.1, the change in temperature of the water was also 4 degrees Celsius. What about the metal? Might as well do this one while I'm here. Well, the metal got cooler, right? The metal started at 111 and ended at 29.1. So the metal got cooler. How much cooler? I take the final temperature of 29.1 and I subtract from that the initial temperature of 111. Use your calculator to check with me, but that turns out to be negative 81.9 degrees Celsius. Negative 81.9 degrees Celsius. So the metal cooled quite a bit. Alright, so remember, degrees Celsius does not measure heat. Heat has three factors. Those factors are the mass, what it's made out of, and how much its temperature changes. These three. So when I take 9 times 2.31 times 4 degrees Celsius, I find out that this calorimeter has gained, because it's positive, has gained 83 joules of heat. So 9 times 4 is 36 times 2, okay, 2 1/3. Alright, so 83 joules of heat. That's a reasonable answer. Now I come over to the liquid. So not only did the calorimeter gain heat, so did the liquid. So when I take 100 times 4.184, remember we're in joules. If it was calories it'd be 1, but we're in joules, so it's 4.184 joules per gram degree Celsius times that change in temperature of 4 degrees. I get to two significant figures because of the 4.0. I'll get 1,700 joules of heat was gained by the liquid. So the calorimeter gained 83, the liquid gained 1,700. That's quite a bit, right? So where did it come from? Again, that's a positive 1,700 because it got warmer. It gained energy. It gained heat. So where did it come from? Energy can't be created or stored, so it had to come from somewhere. So this total of 1,700 plus 83, my rules for significant figures, my calculator is going to tell me 1783, but my precision has to stay to this place, so it's 1,800 joules. So the total gained was around 1,800 joules. Where did it come from? Energy can't be created or destroyed. It had to be released by something. Well, you know, it was released by the metal, right? So come on over here and get, let's do blue maybe, a bright blue. All right. This released 1,800 joules. Well, if it releases energy, remember a positive Q is gaining energy, a negative Q is releasing energy. So the cup and the liquid gained 1,800, which means the metal gave up 1,800. So now, what I'm trying to find is specific heat. All right, remember heat, whoops, I'm running out of space. Heat, Q, equals mc delta T. So solving for C all by itself, that's this heat, divided by m delta T. Well, I just go right up here to my chart. What's the heat? It's negative 1,800. Negative 1,800 divided by the metal's mass. What was that? The metal's mass was 43.2. 43.2. And the change in temperature was negative 81.9. I didn't put units in there. I'm going to do those in a second. All right, first thing I see is a negative divided by a negative. So I'm not even going to put those negatives in my calculator. I highly recommend that you don't, because they often get put in as a minus sign, which is not correct. So 1800 divided by the product. Remember, you need to open your parenthesis, 43.2 times 81.9. Now close the parenthesis. You don't put it like this in your calculator. You put in 43.2 times 81.9, then you close the parentheses so that you have 1800 divided by that product. And that gives you a specific heat, two significant figures of 0.51. Now what would the units be? 1800 was joules, 43.2 was grams, and 81.9 was degrees Celsius. So the heat capacity of the metal we found to be 0.51 joules per gram degrees Celsius. Now, like all on your owns, you're supposed to check your work. We've been having problems with this. Alright, so if I flip the page in my spiral, so I guess I flipped 2 pages, and I go to On Your Own 2.10, I can see all the different steps, but I get down to the end, and by golly, the correct answer is 0.51 joules per gram degrees Celsius. Okay, I hope this helps.